Hi, everyone, and thank you for joining this Jakarta Tech Talk. Today, we have Patrick Duditz, who's going to be sharing his presentation called The Trouble with Data Sharing. So, Patrick, I'll let you go ahead and take it away.
Thank you. Well, welcome, everyone. Today, I would like to speak about the trouble with data sharing. My daily job now is with Bayara. I work as a core server engineer, mostly concentrating on Micro and cloud integrations. And yeah, you can reach me on pretty much any social network via the handle pduditz. And today we'll be speaking about not really technical way, it's a technical issue, more or less an architectural issue. And that one is with this. This is the business for which you are building your IT system, and that system is driven by some data which live in some data storage. The usual constellation these days is, however, that this business information system is split across multiple domains, and each of those domains get their own data store. And when a request enters the system to one domain, very often it happens that that domain doesn't have enough data to fully answer this request. And therefore, it makes a request to another domain. And I'll be referring to this relationship as consumer-producer, so consumer being that the one who needs the data, the producer being the one who owns the data and is responsible for its consistency. And even also, what happens is that even that domain might not have enough data to fully structure the response, and then asks another domain. And as the evolution of the system progresses and new domains are added and new features are added, we discover that there are lots of large or small data dependencies, and that's the trouble with the data sharing I want to speak about today. I look on few technical approaches how this issue is solved, and I look especially on how to make these things consistent and what are the scaling challenges when that, and also what are the challenges when the implementation of the domain changes and this image in the background is in no way complete for any system. There will be new domains coming in, and how to cope with that. Should you have any questions during the talk, please use the button ask a question or put something in the chat, and I will regularly check it and respond it as questions come. Okay, to illustrate the problem, I will be using this example. So let's say we've got kind of video delivery service. So the request for streaming comes in from a user to play a video. So we've got video, we've got a user. And this is a paid platform. So the user bought a subscription. And then subscription gives you access to some collections of videos, and those videos are bundled in collections. And at this point, we're asking, can this user play a video? And we'll be demonstrating those replication approaches at exactly this use case. However, as the time progresses, there will come another use case that a user is homed at some region, and since this is a paid platform, let's assume we are also paying the authors for the video, and suddenly we need to collect how many times a given video has been played in a given region to calculate fees for for authors and for distribution. And this is kind of to think about that the use cases evolve over time, and the data we get for the first request might not be enough to fulfill our future needs. Okay, so what are the troublemakers here? What will cause our trouble when trying to manage that data in distinct data stores? The first one are failures. So either your producing side or your consuming side will be unavailable and cannot progress. Or producer may give you a payload which consumer doesn't yet understand and therefore fails to keep its data in sync or to interpret the response to give further. Another big troublemaker is when you try to modify the same entity in multiple threads or in multiple processes, and we'll see some examples how that might happen and what are the usual outcomes. Since the data is not in the same store, there will be some latency to get it, and if there are multiple networking hopes to get that data, that latency might get a bit unpredictable. And also, if one system tries to determine if one change happened before another change, that turns out to be also pretty challenging in a distributed system. The next troublemakers for data replication is the evolution of the system. We are adding features, we've got new requests for the data, parts of the system get refactored, removed, added, and change their internal representation, which might cause some incompatibilities on the receiving end. Right. Now let's see which approaches we will be discussing today. This is a highly subjective chart based on my experiences before joining Payara. I spent several years with the system that was managing electric vehicle charging stations. We had lots of integrations. All those charging stations were network connected. So in the end, we had coordinate state amongst thousands of nodes. So I personally learned a lot about how things can go wrong when you shuffle data from place to place over network. So we've got three axes here. On the x-axis, there's effort that producer needs to make to be sure that the data he pushes are consistent and consistently received by all the consumers. Y-axis is consumer effort, which means how much effort needs to consumer make for exactly the same goal. That means that he is sure that he got all the data that producer had available. And the third axis is represented by color, and it's infrastructure effort when additional brokers, databases, or coordination amongst the teams or with some infrastructure team is needed, that is signaled by the color. So we'll start with the remote call when the consumer synchronously call producer. Then we go on to push replication when producer pushes the data over to consumer synchronously as they happen. Messaging is kind of middle ground solution where producer pushes the changes about the data into a messaging broker with some short-lived messages. Then we briefly mentioned that we can actually do that the replication on the database level, like we've been able for decades. Another solution is to put all those messages into persistent storage and form some kind of event store. And finally, the example we will be looking at is using pool replication, where consumer regularly ask producer whether there are any new data. All right, no questions so far. So let's look closely on the remote call. So that's a usual solution we are seeing these days. A request comes into content delivery with the user ID, and we ask account service, get me some information about this user, and we'll get back the response and decide upon that whether the user is authorized or not. We see it usually implemented via HTTP RPC, or in very inexact terms, in REST API. I believe cache usually has quite similar characteristics in terms of failure modes. And yeah, it's easy to implement, quite straightforward. We will be seeing some remote calls today as well. There's no big trouble in getting that done. And the positive of this solution, this is the only one that is surely consistent. If you ask the producer for the data and you get back an answer and you understand it, it is surely the correct state of the system at the time of the query. But our enemy here are failures. So the request comes in and we want to ask the account service and it's not there. What to do now? The MicroProfile gives us nice APIs in forms of fault tolerance APIs, where you can define retries, where you can give timeouts and specify how much repeats do you want and what's the upper bound for the failure. However, I think the problem here is that the decision of how long a user can wait until his video is authorized, or whether a user can see a video if we cannot reach the authorization service, is not a development. It's not a question of development. It's not a question of infrastructure. It is really a business question. So if you get lots of these remote calls, and I believe all of them need to be handled by the business side and to decide what the proper failure modes are from the business point of view, you really produce lots of questions towards your product owners, and that's where the effort on the consumer side resides. There is lots of overhead of really documenting all of that and getting that decided. So the negatives are that since this is not self-sufficient, we need to handle all those failures. With each new query that is needed on the data, the producer side probably needs to update their API and add new endpoints. So, for example, for this summary of played videos, there will probably need to be another endpoint rather than just get user, because with millions of videos played per month, there will be quite lots of requests with redundant data. Also, yeah, the fact that each piece of data needs to travel network at least twice in this location, in this situation, gives some bandwidth considerations. Consumers therefore need to handle those retries and fallbacks, and also take account the latency of the remote call. So if the data lives with remote system, it will by definition be slower if it would reside in the same database, for example, or in the same data storage. And also, if you want to count latencies, for example, or some SLAs, these get really hard to compute once you do lots of downstream calls. because those are independent events. So basically your probabilities for given time multiply together. Meaning if you speak to two services with 95 percentile of latency of 100 milliseconds, your 19th percentile latency is 100 milliseconds, because you've got like 5% chance of hitting above 100 milliseconds in the first case and in the second case. Okay, on the side of producer, they need to add new endpoints with every new query to the data. And the most interesting aspect of it is that suppose content delivery is built to handle 1,000 streams per second. What it means that account service, whose major responsibility is making sales to users, need to also handle 1,000 requests per second to cope with the load that is there on the content delivery side. Therefore, the logical next step to take away the scale is to change the flow of the information. So when the subscription changes on the account side, it will speak to the content delivery, let's say again over synchronization TP request as part of the processing of that order. And when the request comes, content delivery can already respond by using its local data that has been replicated from account service. We again usually see that implemented with a REST call or a webhook or a SOAP call. Actually, SOAP calls are quite common also in the other direction. And it's still easy to implement. We solve the bandwidth problem and the network latency problem because we are not speaking that much to the account service, and therefore it scales better. But there are lots of failures. In this case, actually, I think I spent most of the time speaking about troubles on exactly this case because this one just keeps giving. The first one is what to do when one of the consumer systems provided we are replicated to multiple ones. If one of them is unavailable, what to do? Do we stop the upstream request? Do we notify the systems that accepted the change? Sorry, in the end, we managed to roll back and actually implementing distributed transactions within this replication. Or we do we go for lower consistency and we say, okay, there is not so much data, so once a day or once a week, we provide a full load of the data to each consumer, which will work well unless there are changes during processing of that initial load. And then things really get complicated. When we employ retry strategies, we suddenly get into problem recognizing the ordering. And this gives us, this brings us to trouble with time, which is what happens now. So let's assume we've got first request from producer to consumer that changes the region of user 1 to Slovakia, and it happened at timestamp 1, but it failed. In the meantime, the region was changed to Czech Republic at timestamp 2, and then the original request is retried. So if this would be a really interactive session, I would ask which of following may hold for the timestamps. Is the first timestamp smaller than the second one, equal, or greater one, or greater than the first one? And actually, yeah, the answer is, with enough luck, all of those. A is the usual way this happens. So the timestamp at this period at producer was smaller than it was on the second message. However, if this was kind of automated change or a mass change, we hit the trouble that computers these days handle more than one transaction per millisecond, and therefore the timestamps will be equal. And to get the third one, you will need a little bit more luck, because those might be caused by synchronizing the clocks. So the clocks and the computers are alike because they are approximate, and they need to be synced, and that sync can happen in both directions, both forward and backward. So it might be that the clock just synchronized in between those two messages, and suddenly the system time at this time point is smaller than it was at this time point. Or if you are not using UTC in your database, then your favorite night is the weekend of the change from summertime to wintertime, where suddenly thing that happened 1 second after timestamp 1 has become has local timestamp of 1 hour earlier. And therefore, one usually needs to employ some kind of sequence numbers just to recognize in which order the operation happened. But even sequence numbers can have their issues. So let's assume again the same message is sent from producer to consumer, and it's an HTTP request. So here's an HTTP thread at consumer side trying to process the change, and during that processing, that thread gets suspended for whatever reason: garbage collection, waiting for database log, waiting for some unrelated counter or something like that. And as this thread is blocked, we get another request with the second change, and that thread gets luckier and finishes even before the first thread. The contention of the first thread is removed. Therefore, this one completes with no issues, and then thread 1 resumes processing and overwrites the result of the previous thread. So that's usually why you are employing your optimistic locks in JPA. But still you have, you have an issue here. So now this thing failed, and you really need to recognize that it is a message that is already outdated, and no parts of that message is necessary to reconstruct the current state. Okay, so like I showed here, the major problem with synchronously pushing the data from producer to consumer is that it is not consistent. Network failures will result in lost messages. Retries will result in duplicate messages. The fact that it is that those are multiple HTTP requests may result in out of order messages. So consumer needs to be able to cope with all of these, remember which messages it's seeing, prevent concurrent processing on the same entity. You still can handle multiple updates to unrelated entities, and also to be able to decide what happens if it recognizes that the message came out of order. Producer, on the other hand, needs to handle the fact that its message did not reach the consumer, and in the end it will end up building basically a queue. Then still, when we've got new system or new domain joining the system, and it needs the data, it needs another means of getting the data in. So we still need some kind of initial load, even if just not for compensating the fact that the data may become inconsistent, but every new system needs that new data. And in that case, as we are pushing out initial load, we should postpone any other changes to the data to preserve the consistency of the consumers. Right, any questions to these? No. So the next step, right? As a side step, just to shortly remind that there is a possibility that when subscription is changed and stored to a database, your database administrator may set up magical path with which that data appears in your own database. And then you can handle them locally. So it can be done with replicas, or you can employ something like Decomposing to transfer your write-ahead logs from one database and apply it to another, or good triggers to do that. On the positive side, it really is transactionally consistent because that's what databases are good at, and gives you full query possibilities. On the other hand, your data model becomes your API to other parts of the system, which might be a bit hard to maintain in the long term. And still, these replications can fail. In databases, that usually means that your original writes will fail because it cannot be completed fully, or it will fail in some other way. And it might be quite a lot of infrastructure work, probably not for DB admins, but for us Java admins, Java developers. And it really seems like lots of stuff to manage. So this solution is hard on the consumer side because they are the ones that need to adapt. If producer changes their data model, it's consumer that will start failing because the queries no longer return data, or mainly fail to execute because the names changed. Or producer needs to be really careful when changing their data model. There are solutions for that and approaches for that, but yeah, it puts burden on the producer. Whether it's possible to use any kind of DTO to keep the internals hidden. Well, we are sharing database here, so the DTO will be view in this case. So another common approach, and the most common approach in sharing data amongst systems, subsystems, domains, whatever you call them, is messaging. So we've got content delivery subscribing to some topic or a queue, to a message broker, and account will, when subscription changes, account system will send a message to that topic or queue, to that destination. Content delivery receives it, processes it, updates its own internal model with that updated data. All the hard parts of guaranteeing that all participants are available, that there are outstanding messages that need to be delivered. Many of the times, also the ordering of the messages, it's what's taken care of by the broker, so there's less infrastructure code within your application code. Yeah, when the request streaming arrives, it's handled again locally. In Jakarta EE world, we would most preferably use JMS for this task. So even either ActiveMQ or OpenMQ, or we've got different messaging brokers with different standards, RabbitMQ and many cloud messaging services. Those usually implement MQP 1.0. One of the options is to go and use our cloud connectors, which are generic JCA connectors, so we can write message-driven beans that will receive messages from I don't know SQS or from Kafka. So on the positive side, these are decoupled, scalable. Usually, consumer also can filter if there are too many events. It can filter those that the consumer is really interested for. With all the effort broker is doing, there's still a chance of getting either out of order messages or duplicate messages. Duplicate messages usually when consumer fail to acknowledge that it received the message and then fails. Out of order messages can be caused either by the broker, not really common. What is probably surprising, message-driven beans in Glassfish and Payara by default give you pool of I think 10 message-driven beans, so you can process your messages faster. But as we just seen, that's usually not what you want when you are replicating data that may be related. Failure to process a message can result in this kind of poison pill when a message is redelivered endlessly or is then dropped to a dead letter queue. And it is very important in that case to have operations in place to monitor the dead letter queue and understand that your data might get out of sync for that. In some cases, when your queue is limited, you can also block consumer, which can no longer send those messages to the queue or will fail sending the messages to the queue and need to cope with that. So it is important that your queue remains working and all the time, and that you can process anything that's thrown at you. That will require effort for the producer. But first, let's speak about the consumer. Consumer should still be able to identify a duplicated message. When it already seen one, it should know. So it needs to implement this idempotent receiver pattern and limit consumption concurrency. That's the thing with the MTPs I mentioned. If there are no other sources of parallelism in your code. Producer needs to maintain transactional consistency, especially if it cannot send the message. Probably needs to fail the roll transaction so that this information is not lost. And still, if new domain will join the system, it will need different replication means. So we still need some kind of full load replication to handle the new consumers. One of the ways of solving this initial replication trouble is just to store the messages forever, and that's what it's meant with this approach of even storage. So when the subscription changes, it is stored in even storage. And content delivery at any time remembers the last message it's seen from the event store and just reads new events as they are produced by the producer, and then again handles the situation locally. We usually see this pattern with Kafka, but there's nothing preventing you from actually making the table in relational database. Just make sure it is configured properly and that it partitions on the timestamp or something, because it's really hard to delete entries from a table that grows really fast. And similar to messaging, it's decoupled, it scales well. And it preserves history and therefore solves our initial load, or it can serve for auditing purposes as well. On the negative side, well, yeah, infinite storage is not free, so you might need to consider how much data you will be storing, and probably then employing some ways to compact that data by making snapshots or removing some outdated events. And usually these retention rules are handled by the infrastructure, especially in the case of Kafka. So there is some overhead in coordinating those changes. And again, these can be quite large systems, so there might be some operational overhead in running those multiple machines or paying for appropriate service. Similar to how with database, your database storage or your database schema becomes your API, here your events become your API. This usually causes trouble for event source system, where those events need to be source of entire truth, entire state of the system, as those tend to evolve much more frequently, and therefore at the same time taking care of all your consumers that they are still able to interpret your events might be a challenging task. And yeah, but there are multiple solutions to that. Storing multiple variants of the same event, for example, in version 1, version 2, version 3, and so on. But it's what the producer needs to do to guarantee that events that it once written are still mean the same thing. And consumer needs to be able to recognize multiple versions of events and interpret them properly. Limiting consumption concurrency in this case is probably a node towards Kafka, where its topics are partitioned into multiple partitions. So you should select a proper business key, meaning that events related to one entity always land in same partition. All right. So we are getting towards the end. We are getting toward actually seeing some code. And pull replication is variation of the event store. And we basically build the event store inside the producer database. That's the gist of the solution. So when subscription changes, we've got this event that we store within that same transaction into accounts data storage. Content delivery remembers the last event it's seen from the account and will pull regularly the account service for the new events and process them. Doesn't seem like much of the change, but actually it makes things quite simpler. One thing, I didn't find any library to do that, but as you'll see, by combining few standard features of Jakarta and MicroProfile, it's pretty easy to do. It's quite simple. It's transactionally consistent because the event is only written if the entire transaction succeeds. The sequencing is handled by the consumer, and you will ask for the range of events, so you know that those events that you get over the wire are exactly in that sequence in which they've been written or sorted, at least. And the whole handling of retention remains on the producer side. Also, all of the evolution, event transformation, upcasting, downcasting, it all remains on the consumer side. So it can guarantee that compatibility better than shoveling that data outside of its control. We still have a problem to solve, what to do with the storage or large amount of events that need to be compacted. And compared to other solutions, this probably have quite high latency, because you will not be asking the account service for new events every millisecond, because we are back to the beginning and handling 1,000 requests per second. So it will take some time for that data to appear on the consumer side. The producer responsibilities here is really to handle all the data and make it compact, and being able to scale when there is lots of events or lots of consumers that would want that data. This is where, in some cases, again, the replication of the events might kind of be majority of the time a producer will spend with, rather than handling user requests. Consumers need to be, again, aware of the unknown payloads when the producer breaks their promise and produces an invalid event. This is, again, something that needs to be monitored in the same way like it is monitored, or it will be monitored as a dead letter queue in messaging system, because when you've got a message you cannot get through, you get stuck on that point, and your data stores diverge. And then there's pretty easy task of handling cursor storage. All right, let's see that live. The code for the data is available over at GitHub, and I would post that somewhere. Now allow me to fix my browser. All right. So let's see a demo here. I've implemented similar solution to what I discussed in the presentation. So in this column, we've got the account system that has a list of users. So we don't need that. Here's me. And nothing is happening. All right. Okay, something is happening. But probably the streaming is playing a bit with my browser here. And I did hit a refresh in the meantime. So okay, eventually we arrived at something. I created a user and accountant system, and we can handle the subscriptions it have, but it doesn't know about any subscriptions. So let's create one. Let's create subscription 1. And let's add some video to it. Let's call it Trouble with Data Sharing. So at this point, we will make this query. Is this user, Patrick, able to work with this variety of trouble with data sharing? The response is forbidden. And over here, we see the last event on the producer side, the last event read on the consumer side, and last time of sync. The poll is now set to 15 seconds. So every 15 seconds, it will the content delivery will poll the account service for the new data. So we'll now add the subscription to user Patrick. And we see that this event did happen. Don't ask me why you are seeing that 4 times. But in the meantime, another synchronization happened. And suddenly, since this user has access to subscription 1, and subscription 1 contains this video, trouble with data sharing, everything is good, and the video can be accessed, or could be accessed if there would be any video. Okay, how did we do that? So the front end is written in Vue, and we will not be discussing that at all. We will look on the good old backend code. If you look at the code, I will write the path to the repository at the end of the talk. So we've got a consumer application here. We've got this demo which hosts the front end, and we've got producer app, which is in this point this account management. So let's start in the account management and see how we are creating the user. We just use plain JPA code. We create a new user entity, set its attributes, so the name and the ID. We persist it, and then we fire a CDI event. User will generate this nice user-created event saying which user ID there is. I added like a lot of hierarchy for the user event. So we've got user created, user deleted, subscription added and removed. So those operations that you could see on the screen. So we fired that event and CDI because we don't want this to be bound really strongly to the act of creating the user. And we might have other subsystems within an accounting system to react on the fact that a new user is created or signed up or whatever this means. We've got one observer on that event, which will take that event and store it in a database in a form really trivial. We store the ID as kind of auto-generated sequence. We store the event type and the JSON payload of the event. So, and we store that. We require that this happens in the transaction, of course, because we need the transaction to store the data. At this point, I would like to note one pitfall. When you do observing in CDI, there's this during, and in progress as the default value, which means do it now as the transaction is running. I thought it would be a great idea to do it before completion, so I know that the database would commit. However, that point of time is too late to do any changes to the database that I've been doing. So default is quite all right for this. So as we created those events, they remain in the database, and they are available with this simple replication endpoint sitting on slash replication. So we will basically call get to that replication and pass the last ID that you've seen as a consumer and how many events you want to get. And we'll just, you do trivial named query, and replication event handles its serialization back. So this payload is a JSON string, so we need to reparse it and create JSON even and make it JSON again. So it will be in this form that you've seen here. User created. That was okay. This is the ID, this is the type, and this is the payload. So user ID and the ID and subscription added, and edit the subscription. Let's just delete the subscription. I've got something moving here. I really wonder how I made those 3-4 subscription requests on the front end to do that. Since we removed the subscription, we are back to forbidden. So back to code. What's happening on the side of the content delivery? How it gets its events, how it gets the answer. The answer is simple, because it's again a named query where we are joining from user to the subscriptions to the contents where we are looking for the content, whether it belongs to a subscription that user has. So that part is easy. However, how do we get the data? This is handled by simple EJB with a schedule every 15 seconds poll for new data, and the poller has this single cursor class, which is really minimal entity with just 3 fields, even not public, and doesn't have any methods. It's only used for this replication, so I didn't put like lots of ceremony around it. We guarantee that the cursor for the user's replication exists, and then we go and fetch it. It's also quite straightforward. We update the last time we tried to fetch something. And then we call account service. And for that, we are using a MicroProfile REST API, REST client API. So this is the description of that HTTP endpoint. We do get with query parameters ID and size. If you compare, that's exactly the interface this fetch method has. So get method with ID and size. And the runtime will generate REST client for us and handle transforming from this call to actual usage of Chuck's REST client and getting the data back. The replication event we are getting here is a bit different than what it is on the account side, because that's natural. Different domain has different needs, different representations. So on the account side, we had actual hierarchy of objects. On the receiving side, we've got an enum that basically corresponds to those various types that exist there. And we've got generic payload because we happen to know that we only care about user IDs and subscription, and we don't need to build any complicated object hierarchy for that. But that can be different in every use case. So once we fetch the data, we just note how many events we seen last time, and then we use these enum of the event type as kind of strategy on how to interpret that payload. So if it was a user created, we know we should create the user. If it was user removed, we know we should remove the user, and so on. So this is how we do the data synchronization. So there needs to be explicit code for every change, depending on how you define your eventing protocols. Okay, Miroslav asks, if store event methods store event to Kafka topic with very long retention period and client was Kafka client, are all those approaches almost the same? Yes, they are. They are almost the same. The difference is that once you send something to Kafka client, you cannot change it. Whereas here you can evolve your internal events, or you can provide endpoints for downcasting the events to previous versions, even if you already stored the new ones. So the only difference is that the owner of the data is in control of access to the data. It didn't put it away to a messaging broker or to Kafka. Yeah, more control of history, more control of access. Thank you. Okay. So we process our replication events, and with those methods, the data is in database of content delivery, and this is how it is handled. All right, let me just quickly point you to the code repository. This is the URL if you are interested. Okay, infrastructure-wise, this has been running on Kubernetes cluster in Azure, so those are actually deployed as separate applications. And yeah, if you want to put some bad data in, it's replication demo.pyara.app. Okay, let me switch back to the talk. I think code-wise, there is not much to tell. The code should compile itself without problems, runs with the latest PyraMicro. Yeah, should you have any questions, you can contact me afterwards or via any social network. Okay, so yeah, this is pretty basic. So still for production level, there will be like a little bit more stuff you would like to do, which is things concerning event evolution. So if you want to change the representation of your event, you might be rebuilding your table and having an endpoint that could still deliver them in the older version. For example, you might have more control on how things are serialized, or how to store those events in compact form. It doesn't necessarily need to be changed events. Those can also be snapshots, but if you order those snapshots, it will be it can serve as a really effective way of transferring the changes. So for each entity, there will be one snapshot you can get, but still that last seen event ID could serve as a point in time concerning which changes you've seen already and which you've yet not seen. And also polling improvements can be improved, so there can be additional WebSocket channel from which the producer can inform the consumers. Yeah, now it's a good time to look for some new events. All right, so in conclusion, think very carefully whatever of those approaches or combinations of those approaches you are using, what can happen so you would lose the consistency of your data. Because, yeah, those things always happen on Friday afternoon. If possible, keep your replication code paths single-threaded, not only within your process, but within your entire domain, or very carefully sharded according to the business key so that you are not changing the same entity into threads. And I think this approach of using pull replication is really underrated, as it is simple and one of the most consistent ways to get data between two systems. So thank you. I hope that was interesting for you. If you've got any more questions, please ask now. And if you're interested in Payara, go and download our software. And if you are interested in our other activities with open source community, please have a look at join Payara Reef, which might help you growing your community. Thanks.
Awesome. Thank you so much, Patrick. And thank you to everybody for joining us. This is going to be posted on YouTube tomorrow. So keep an eye out for that on socials. And we'll see you at the next Tech Talk. Take care.
Thank you. Thanks for having me.